My friends. So instead of just giving it to you, what I'm going to do is come back and fill this in after we've proved it. So we'll kind of discover this formula through its own proof, okay? And this is a kind of an outline of a proof. It's not super formal. So to explain why the formula looks the way it does, what you could actually do is you could start with, instead of an infinite geometric series, you could start with a finite geometric series. And we're going to do one that has n terms in it. So the number of terms is n. And so this will just be like a term-by-term expansion, nothing fancy, not a formula or anything. So, what would the first term be? Well, generic for first term is a sub 1. And then your second term would be a sub 1 times your common ratio, because it's a geometric series. Your third term would be a sub 1 times r squared. Now notice something, the next term is going to be your fourth term, right? But it's a sub 1 times r to what power? That's right, just 3. So it's your fourth term, but your power on r is 3. So you would continue in this manner until you get, let's leave a gap here, until you get down to your nth term. So what do you think the nth term would be? Well, it would be your first term multiplied by your common ratio, n minus 1 times. I hope it makes sense. This was your fourth term, but you had a power of 3. This was your third term, but you had a power of 1, etc. And what term would be right in front of it, your n minus 1 term? Well, it would be your first term that got multiplied by your common ratio, n minus 2 times. Hopefully that makes sense, everybody. Okay, so this is a term-by-term expansion for for a finite nth partial sum, essentially. So now a fun trick that helps you get where we want to go is to just multiply both sides of this equation by r, where r just means the common ratio. Well, on the right side, you'd have quite a bit of distribution to do, right? You'd have to multiply each term by r. So what would a sub 1 times r be? It would be a sub 1r. And so I'm going to line that up with a sub 1r in the top row. And what would a sub 1r times r be? Yep, it would be a sub 1r squared. And multiplying each term in the previous row by r. So like take a sub 1r to the n minus 2, multiply it by another r, you get a sub 1r to the n minus 1. Take a sub 1r to the n minus 1, multiply it by another r, you get a sub 1r. And then I did leave a mysterious gap here to be filled in. Whoops, let me stop scribbling. I left a mysterious gap here. Well, that would have come from this term that was right in front of a sub 1r to the n minus 2, which would have been a sub 1r to the n minus 3, and multiply that by r, and you get a sub 1r to the n minus 2. And now that I've got this all nice and lined up, what on earth are we going to do? We are going to subtract both rows. How come? Because I've done this before. Okay. Anyway, so let's subtract this second row. Well, on the left side of the equation, we would just have s sub n minus r times s sub n. And on the right side, you'd have a whole bunch of like terms that would vanish out, like this. And so all of those terms vanished out. And so after all that destruction, who would be left standing? Well, a sub 1 would be still in your expression, and you would have minus a sub 1r. So all this term-by-term expansion stuff just got way simpler. And not only that, but if you've been sufficiently tortured in algebra classes in the past, you're going to really feel a strong urge to factor out common factors in the stuff that's left. For example, on the left side, we could factor out s sub n, and we'd have to multiply that by 1 minus r. And then on the right side, we could factor out a sub 1, and we'd have to multiply that by 1 minus r. Oops. Whoa, to the n. Oh no, that was important, to the n. I knew that looked weird. Okay, anyway, hope it makes sense. There's an n there. All right, next, we would have to, if we were trying to get a formula for S sub n, instead of having to do it term by term like we had in the first place, you could just divide both sides by 1 minus r. So we'd have a formula that would be for an nth partial sum. So it's not an infinite sum yet. It's still an nth partial sum. Well, so this is a formula for an nth partial sum. Truth is that other than kind of moving through this to get what we want, in this class, we don't have much use for that particular formula. But what would we need to do to that expression to get an infinite sum? Well, we need to let the number of terms approach infinity. Well, what letter represents the number of terms? It's n. So let's think about, what if we let n approach infinity? This is the only place in this whole expression where you have n in it at all. And I hope it makes sense that if r isn't between -1 and 1, then you're going to get some insane answer for this expression. But let's look at if r is between -1 and 1. Then what would the limit as n approaches infinity of r to the n be? Well, if r right there is between -1 and 1, you multiply it by itself infinitely many times, it's going to go to 0. So if that happened, then what would we have if that whole term approached 0? Well, we'd have an infinite sum of a geometric series, and on the top of the fraction, you'd have a sub 1 times 1 minus 0, which would just be a sub 1. And then it would be divided by 1 minus r. Oh man, guess what? That's the formula. So up here, the formula would be, it's just your first term divided by 1 minus your common ratio. And considering how messy the derivation was, it's kind of nice that it turned out that cute. But we have to keep our grimy mitts off that formula unless we have formula or r value between -1 and 1. Otherwise, you would just use your common sense in expanding things out. So with that said, let's go back to example 1 and practice using it. So for part A, you had an infinite geometric series. Your common ratio is 1/2, which is between -1 and 1. And so according to the formula, your infinite sum would have equaled your first term, which was 16, divided by 1 minus your common ratio, which was 1/2. Well, that would be 16 over 1/2. Flip and multiply, and you get the 32 we thought we were going to get. And for part B, if we were to use that formula, it would tell us that the sum would equal your first term, 1/8, over 1 minus your common ratio, which is 2. And if you simplify that, you get -1/8, which makes no sense at all. And how come? Well, because we shouldn't have used that formula in the first place, because your common ratio was 2, which isn't between -1 and 1. There we go. All right, my friends, you need to memorize that formula if you haven't already, okay? I know at one time a lot of you had it memorized. Time to rememorize it if necessary, okay? All right, let's take a look at example 2. The directions are for you to determine whether each sum is geometric, and then you try to evaluate each one, whether it's geometric or not, okay? See what you can do and check in with me in the next video.